Organic Chemistry at the Pool.
By Lauren Glass,
Toni Adetayo,
Ben Rentz,
and Austin Banks.
Hey! Come on! Hurry up! I want to go to Pirates Plunge!
1 second, sweetie. We're going on all the rides today. We're doing them all. Have fun.
Are you making a sissy?
No, I'm not.
You know they put a chemical in the pool that turns urine blue.
No. It's an old wives' tale, sweetie. It's an old wives' tale.
Oh my God! You're humiliating me!
Swimming is an activity enjoyed by millions of people across the world. It's a fun way to spend a hot summer day, and it's also a competitive sport. But nobody thinks about what we're bringing with us when we enter the pool. While there's not actually a chemical in the pool that turns our urine blue, there are a lot of other reactions happening all the time in the pool. Recent estimates show that averaged out, every time a person goes into the pool, they bring with them about 0.2 to 1.76 liters of sweat, which could almost fill up a 2-liter bottle of soda, and 25 to 117 milliliters of urine, which could actually fill up about half a cup.
so what's in our pee?
That's a good question, Lauren. The solutes in urine are made up of 38% inorganic salts, 51% organic compounds, and 11% organic ammonium salts. Of the organic compounds, urea is the largest component, making up 72%. The next largest is creatinine, which is 8%, and the third largest is tyrosine, which makes up 2%. The remaining 18% are compounds such as sugars and amino acids. This video is going to focus on the 3 most prevalent organic compounds in urine: urea, creatinine, and tyrosine.
Hey Lauren, tell me more about urea.
Urea, shown here, is a waste product from the kidneys. It has 2 primary amine groups and a carbonyl group. The 2 broad peaks between 3300 and 3500 are indicative of the 2 primary amines in the molecule. The sharp peak near 1700 demonstrates the presence of a carbonyl.
Austin, so what about tyrosine?
That's a good question, Ben. Tyrosine is an amino acid typically used in the synthesis of proteins. The IR spectrum shows a collection of broad peaks centered around 3,000 inverse centimeters. The broadness is a result of extensive hydrogen bonding, both inter- and intramolecularly. This causes peak broadening, as well as many functional groups which absorb in this zone, such as amine and alcohol, which absorb around 3,300, sp3 hybridized CH bonds, which absorb slightly lower than 3,000, as well as sp2 hybridized CH bonds, which absorb slightly higher than 3,000. The sharp peak, which is fully resolvable near 1,700 inverse centimeters, demonstrates that the molecule contains a carbonyl.
Ben, can you tell us more about creatinine?
Sure, Lauren. So creatinine is a waste product produced by the body's metabolism. The IR spectrum shown here shows broad peaks around 3,200, indicative of the primary and secondary amines found in the molecule. There's another sharp peak around 1,700, indicative of a carbonyl. The peaks below 1,600 shown here are probably the result of a conjugated ring system.
So Ben, how does your pee relate to organic chemistry in the swimming pool?
Well, Lauren, as we mentioned earlier, there's a lot of people in the pool and they're all introducing a lot of bodily fluids. This can negatively impact pool chemistry and possibly spread disease. As a result, public swimming pools are typically heavily chlorinated to prevent this. The chlorine molecule, or ion, can kill microorganisms such as bacteria by breaking down the cell wall and destroying their inner enzymes or proteins.
How does chlorine get into pools in the first place?
Chlorine may be introduced as an aqueous solution, a salt pellet, or even in old pools chlorine was bubbled through as a gas. And from this, many reactive compounds can be found in concentrations high enough for reactions to proceed in swimming pools. These reactive compounds include hydrochloric acid, hypochlorous acid, depending on the pH you might see hydroxide ions, and also molecular chlorine. These chlorine compounds can react with urea, tyrosine, and creatinine from your pee to form some interesting products. So Ben, can you tell us more about reactions that happen?
Sure, we'll start with urea. Urea, which if you remember makes up 36% of urine, will gradually decompose in a pool when it is exposed to chlorine. In this case, hypochlorous acid. A number of different products can form during this decomposition, including carbon dioxide, molecular nitrogen, hydrochloric acid, nitric acid, and water. Unfortunately, these reactions have not been studied in great depth, and the actual electron pushing mechanism for these reactions are not fully understood. However, we are aware of many additional side reactions that can occur with these products in swimming pools and many additional chemical compounds that have been detected in swimming pools, such as nitrogen trichloride, which, as you can tell, has a trigonal pyramidal shape, and an sp3 hybridized nitrogen because of the 4 regions of electron density. This can also cause acute lung damage in people exposed to it. Additionally, hyponitrous acid can form, which is an explosive compound and can theoretically be found in both a cis or a trans isomer.
What was that second most prominent compound again? Creatinine? Yeah, what reactions does that one undergo?
So creatinine reacts with chlorine to form creatinine chloramine, which may then further react to make several different compounds. But before I get to that, I'll show you how creatinine forms creatinine chloramine using some of the concepts we have learned in class. First, creatinine tautomerizes so that it transforms its group that appears to look like an enamine to a structure that contains a group similar to an amine instead. Next, a proton transfer occurs when hydroxy ion attacks the hydrogen of a secondary amide and gives the nitrogen another free pair of electrons. The nitrogen can then donate these electrons to share with a neighboring carbon to form a double bond and push the electrons from the double bonded nitrogen to the nitrogen, making it a strong nucleophile. These electrons can now attack the chlorine atom in the Cl2 and break the chlorine-chlorine bond, which now then makes creatinine chloramine. Creatinine chloramine can further react to form products such as hydroxycreatinine chloramine, N-methylglycine, urea, methylamine, and formaldehyde.
Okay, my turn. Let's talk about tyrosine.
Go for it, Toni.
When tyrosine is in the presence of hypochlorous acid, multiple reactions can occur. One of these reactions is the chlorination of its aromatic ring, where the hydrogen is substituted for a chlorine atom. If you were paying attention in your Orgo class, you'll remember that both the hydroxy group and carbon chain substituents are activating groups. That means that the chlorine will add to either the ortho or the para position.
But wait, if they're both activating groups, how do we know where the chlorine will actually add?
Now that's a great question, Ben. I'll tell you right now. Since the OH group is a stronger activating group, the chlorine will prefer to bind to its ortho or para position. Since the para position is taken up by the carbon chain substituent, it's going to prefer to add to its ortho position. And that would form chlorinated tyrosine, or 3-chlorotyrosine. And if further reacted in excess acid, we would form dichlorinated tyrosine. All right, we're running out of time, so let's wrap this up.
Now, we've seen some products that can result from the 3 major components of our pee reacting with chlorine in pools. Some of the products that we mentioned are harmful, such as formaldehyde, which is toxic, and trichloramine, which can damage your lungs.
And no, we have not made any of this up. All of the mechanisms shown in this video have been taken from published and peer-reviewed research articles, and they can be found at the end of this video.
So next time you jump into a pool, hopefully you'll think twice about skipping that pre-swim shower and that long walk into the bathroom. All thanks to a little organic chemistry.